So in the last class or last two classes, we have talked about different features of Prolog, and we were kind of analyzing different category of problems, right? So the last category that we will be talking about is the category of problems that belong to combinatorial optimization. So we are in the category combinatorial optimization. So one such problem in this category is a knapsack problem, which I guess has been discussed in the previous classes. To bring everyone on the same page, let me give you a very brief overview of this problem. So this problem has got two versions. One is a decision problem. And what is the decision problem? Can any one of you tell me? Hello, there is a bit of noise. I could not hear you properly.
Sir, so the discipline part in the knapsack problem is to basically choose which next element to put in the bag given the current state of the bag.
No, actually, that is not a decision problem. So there you are talking about you are in a state and you are applying an operator on that state, whether to include one item or not. And if you do that, then you transit to a different state. So that is not really the problem. So there you are trying to solve the problem, right? So the decision problem goes like this. So let us define a few entities. So first entity that I like to define is the set of items. So basically you have a set of items and for each item you have a corresponding weight. So W contains the corresponding weights of the items. And let's say C is again another set which is basically corresponding values of the items. Values. So every item is associated with one value and of course a weight. Now you have to design or define a knapsack which will have if we add the items in the weights of the items in the knapsack, that will give you a weight. And the knapsack has got a capacity. So this has got a capacity limit. So it cannot hold items beyond this capacity limit. So the addition of the weights of the items that are there inside this knapsack should not cross this capacity limit, right? And of course, our goal is to say have at minimum a kind of consolidated value. Right. So let us try to instantiate this problem with an example. So what you have got, say, one pantry. In the pantry, you have got different foods. And each food has got kind of weight. So I can define the food items consisting of it will be having a name, of course. So the name, it is having a weight and the corresponding calorie value. So this is the weight and calorie value. So what you want to pack as much as possible in the knapsack so that your capacity does not exceed the capacity limit, and you want to maximize the calorie content, right? Now in the decision problem, what is given? You are given with this S you are given with K, you are given with this capacity limit, and you are given with a calorie goal. So how much calorie at minimum you want to pack, right? So given this, either it can output yes or no. So yes means that the given knapsack, the given configuration satisfies this current goal, but does not cross this capacity limit. But if the reverse happens, then the output will be no. So let us try to formalize it a little bit. So you have K. So K is a kind of subset of S, right? K is a kind of subset of S. And what you want to have as constraint? As constraint, you want to have, say, one item for all the items belonging to K. The sum of Wi should be less than equal to your capacity limit. Right? And the other constraint is that for all the items in the knapsack, if you sum up the calorie content, it should be greater than equal to calorie goal, right? So this is the formalization of the decision problem, right? Now there is another version of the problem which we call as the optimization problem. And in the optimization problem, what do we have as argument? We have got this S. You have to find a K. So this is not given. This is not given, right? So that it does not cross the capacity limit. And of course, the goal is not given. You want to maximize the total calorie content. This is what you want to maximize. So if you want to write this in a formal notation, how do I write this? So basically, I want to maximize. CI subject to I belongs to K, Wi should be less than equal to your capacity limit. So this is more or less the formalization of the two types of problem. One is the decision problem, where our output will be yes or no. And for optimization problem, our output will be K, for which the calorie content is maximized. And of course, you need to satisfy this constraint, this particular constraint. So let us try to see how do we solve these two problems using Prolog. So is my browser visible? Just give me a hint.
Yes, sir.
Yes, sir. Yes, sir.
Okay, good. Thank you. Just give me a moment. Well, so the first thing that we need to specify is to find out the possible subsequences, right? So this subsequence extraction will not be used in the decision version, because we know that our input is a knapsack. So here, using this subsequent predicate, we are trying to extract all possible combinations of the items, basically all possible knapsacks that we can build with a set of items, right? So that will not be required for the decision problem, right? Because that is we are doing this for a given knapsack. Now this function, this predicate or this rule, what it is doing, this is trying to uh, mm, find out for a given knapsack, what is the total weight. So let us try to see how we are doing this. So we have a predicate like food, the food name, the weight, and the calorie. So the third one is the calorie, right? Now it is a list, right? Your knapsack is a list of food items, right? So you pick up the first food item, we have the rest of the item, and we call the same function to compute the weight of the rest of the knapsack, and whatever we get out of that, we are adding that with W, which is the weight of the current item, and we are assigning that summation to X. So this is very straightforward. We have done this kind of programming earlier. And similarly, for calorie, we will be doing the same thing. Only thing that will be changed here, we are using the third argument of the food predicate. And the first two argument we are setting as don't care, because we are interested only on C, right? And finally, what you have this calorie to be computed, right? Now, how do we go about the decision problem? As I mentioned earlier, we have got four arguments: the pantry, which is basically the set of items; the capacity limit that you want to have. Basically, your knapsack has a limit; and goal, the calorie goal that you want to achieve; and finally, this is the knapsack that we have entered, right? So first of all, we'll check that whether this given knapsack is a subsequence of pantry or not. So, so I'm using the subsequence predicate here just to check whether this knapsack is a valid subsequence of pantry, right? We need this, but we will not be extracting all the knapsacks here. We just will be checking.
Sir, I have a
Yeah,
doubt.
yeah, sure.
Sir, can you explain the subsequence predicate once?
I'll do that. I'll do that.
Okay.
So basically, for now, you assume that this subsequence, what it can do, if you have two instantiated list, so this knapsack is an instantiated list and pantry is also an instantiated list. We are just checking whether knapsack is a subsequence of pantry or not. Now, subsequence for the normal sense, what we do, we take into account the consecutive item. So here we are not doing this really. So let's say, let me type in here. So let's say we have list like this. So this is your pantry, right? So what are the subsequence that we can extract? We can extract the empty list. We can extract this to be one subsequence. We can extract, say, 1, 2 as subsequence. We can extract, say, 1, 3 as subsequence. And we can extract, say, 2, 3 as subsequence. So does that make sense?
Yes, sir. Now
Okay.
I got it.
Yeah. So we compute the weight for this knapsack, and we check whether this is less than the capacity that we have set. And then we compute the calorie for this knapsack, and we compute whether, or check whether this calorie that we have computed is greater than the goal or not, right? So if we do that, if all the sub goals are satisfied, then this knapsack decision for this given argument will be satisfied, right? So, I think this is more or less on the the decision problem. So let me check whether I have saved this. Yeah. So this is the, okay. So this is the optimization problem. Let me change it to decision. So for decision, we need to provide the end. So this is your entire list. So this is your entire pantry. Then the second is the capacity, right? Your capacity is, let's say it is 4. Then you need to set a goal. Maybe let us set a goal, say 11,000 11,200 calories, right? And let us define the knapsack to be, say, the first two items, right? So if we run this, so it is saying false because, you know, if we add these two, this will cross 11,200, right? Now we can set this up to say 15,000 and check again. So, okay, so one other goal is not satisfied, which is basically the capacity is not satisfied, right? So if we take another category, another combination, maybe say this two. So we have taken two others in the knapsack. So peanut butter, and let us check. So we are having false again. Why is that?
So calorie requirement.
Calorie requirement is crossing, right? So this be no.
So lessen the calorie requirement.
Hello, yeah.
So the calorie requirement means it's too much. We have to lessen it.
Okay, okay, sure. Yeah. I got it. Right. So this is more or less the idea. Thank you. Now let us go to the optimization problem. Okay. Now for this, I think I have already explained the subsequence. So you might want to have a look at it, how they are computing this. This should be straightforward. Let me go directly to this knapsack optimization. So let us see what is the strategy. So what we will be doing here, as we are not given with the content of the knapsack, which we want to really come up with. So let us first define what do we mean by a legal knapsack. So what is the meaning of a legal knapsack? So whatever knapsack we have, that knapsack should be a subsequence of pantry, right? And let us compute the weight of the knapsack, and we need to check whether this weight is less than the capacity or not, right? We are not solving the maximization problem yet. Only we are checking whether a knapsack is a legal knapsack or not, right? Now look at this predicate carefully. So this is a built-in predicate in Prolog, which is called find all. So let us see what are the arguments here. So here, as you can see, we have put a goal as the second argument here, right? So here what we have, you have pantry, capacity, and K. And basically what we are checking that a K, whether that is a legal knapsack or not, right? And this list is basically, pantry contains what? It is containing the list of items that we have in our pantry. Now, what might happen if you run it once, then if you run this legal knapsack once, it will give you a combination, right? Depending on whether the total capacity of knapsack is less than equal to W or not. The total capacity is less than equal to capacity or not, right? Now, it might be having several such instantiation. So now, if you look at the computational model of Prolog, so after it computes one such value, it will go back and do backtracking to find out other entries or other values of K, right? So here, what we are trying to do, we are trying to list down all the knapsacks which are legal knapsacks. Now, as these are being computed in different branches of search, we cannot store them directly in a list as we did earlier. So that's why we are using this predicate find all. So what it does, it takes this K and putting all the instances of K into the list L. So what this list L will contain? It will contain all the legal knapsacks that we can compute. So let us look at the flow. So first, we are computing all the subsets of this pantry, right? And whatever subset we are getting, we are checking whether the weight of the subset is less than capacity or not. If that is satisfied, then that knapsack will be made an entry into this L, right? Now, in L, what we get all the possible legal knapsacks. Now we have to do the optimization operation. So here we are doing this optimization. So doing this optimization is very pretty easy, right? So what we'll be doing, we'll be taking each knapsack entry from L and compute the total calorie for that particular entry. We'll be taking the next entry in the knapsack. We'll compute the total calorie for that knapsack and we'll check with the previous maximum value. If the next if the total calorie of the next item or the current item is greater than the existing max, then we set the max to be a new max. Otherwise, we'll keep it as it is and we'll go on processing the next part of the list, right? So does that make sense?
Sir, so what is the syntax of the find all calories function?
Okay.
Predicate.
Okay. So whatever we will be putting here in the so any variable. So this first argument here in the find all should be a variable from the goal. The second argument is the goal, right?
Yes, sir.
Now, whatever instantiation that we are having in K, I'll be putting it here, right? Or it can be a combination of different multiple variables that appear in this particular goal. But for this particular problem, we are just happy to note what is the knapsack that is legal, right? And the third argument is a list. You can name it anything. What will it contain? It will contain all the legal knapsacks that we have computed using this code. Okay, so the middle one is the goal. The first one is either a variable or a combination of the variables that appear inside the goal. And the last element is a list which will accumulate all the instantiation of the variable combination that you are putting in here. Right?
Yes, sir. Got it.
So any other doubt? So now this max calorie part is pretty straightforward, right? So I'll just request you to check this predicate, which is basically computing the max calories value. And the idea is same, like we are processing the list sequentially. For the first item, we are first computing the max value or the value of the calorie, total calorie. And as we go on further, we keep on maintaining this max value, right? As we find maximum in a list, right? So I think that's it for this knapsack problem. So let me go to the other problem, which we call as n-queen problem. So I guess this n-queens problem has been discussed earlier. So should I explain it further or I can just skip the description part? Will that be fine? Just give me a hint.
Sir, I have a doubt in the knapsack problem only.
Okay, tell me.
So in the way we solved the knapsack problem, we were finding all possible subsequences, right? So will not that be a bad time complexity? for the
Yeah,
knapsack?
so here you have raised a valid point. Here we have not really used any heuristics and others, right? As we did in Aster and similar algorithms, right? So for a better implementation, I think we should go for those particular algorithms. And let me tell you, the search algorithms, they can also be implemented using Prolog. So that can be done, but you have raised a valid point. But it's a very fast-hand and naive way to implement knapsack problem. I take your point.
So can we use the decision problem to solve it in a better way?
So what is your idea? Let me know.
So suppose we have a valid, so can you just show that page?
Okay. Yeah.
So the decision
Mhm.
predicate, yeah. So suppose we have a valid knapsack decision, pantry capacity goal knapsack. So our next knapsack decision will be something more, the where the goal will be more, if we find like that. So
So actually, the problem with that approach would be, uh, so the way Prolog computes the decisions or the values. So first it follows a branch of reasoning, right? Now, after it gets a satisfaction, then it goes for the other instantiation, right? So as we are going for the other instantiations, the earlier values will be lost, right? So the maintenance of these previous values or previous combinations will be very cumbersome to manage uh, manage like writing the explicit predicates, and the exactly the same thing is being done using this find all predicate. So we have just taken a shortcut. We are doing the similar thing that we have mentioned, but here we are uh, putting the burden to this particular function find all. So your point is, I compute a decision, then we compute the value and keep that value, and then we compute another decision, then we compare the value. So you see, maintaining that will be very cumbersome, right? And this is a very easy way to manage that complexity, right?
okay, so
Okay, good. So let me go to NQueen's problem. So if we just have a very brief overview of the problem. So we have got, say, n queens in a kind of n cross n grid. You have to place them in every row or every column so that no two queens attack each other, right? The definition of attack is either they are on same row, same column, or they are on the same diagonal, right? So the first question that we should be asking while we are trying to code this in Prolog is, how do we represent the placement of the queens, right? I think those are the variables that we want to have the values for, right? So we have got 8 queens. So let us take the 8 queen as an instance. So for 8 queens, we have got 8 values that we need to fill up, right? So, and what would be the values for each such entry? So basically the coordinate of this chessboard, right? So the first idea for representation would be, can we have a predicate like this? Queen xy, where x is the, say, this is your x coordinate and this is your y coordinate, right? Now the point is, well, we have got only one kind of piece. There are no other pieces like pawns and, say, rooks and others. So I can really do away with this. This is redundant, right? So we can just represent this. So the way to represent this combination of values in Prolog is you can represent them like this in a symbolic form. So this is not a division. We are just maintaining two values x and y, right? So if we just say 2, 5, say this is your 2 and 5. So let's say we have a configuration like this and say 3, 7 and say 6, 1. So this can be represented as 2, 5, say 3, 7 and 6, 1. So this assignment, but you have to assign 8, right? So what we want to write, we want to write a predicate, say legal. So what is X? X is basically this entry, right? Now what should be the structure of legal? Any idea? So what do we need to check first? Given a list of assignments, which is basically X, you take out the first element, right? Say X1 and the rest. Whether X1 is having a attack with any of the elements in this rest, right? So let us pick up this 2, 5. So I'll check whether 2, 5 assignment is having any contest with this assignment and this assignment. If that is not, then we say this is a legal assignment, right? So let us go with that approach, if that makes sense. So that's why we define a predicate which we call as no check. So what no check will do, as I mentioned earlier, that XY, which is the current assignment, and this is the existing assignment, and we'll be taking each element from this existing assignment and check whether that is legal or not. How do we define legal? They should not be situated on the same X coordinate. So this is how we are making sure that they should not be placed on the same Y coordinate. And this is checking for the diagonal, right? So the absolute value of Y1 minus Y should not be equal to the absolute value of X1 minus X. That will make sure that they are not attacking diagonally. And if that is so, that means there is no contest between this and X1, Y1. Then we'll go for checking XY with the rest, right? And if we have a condition like this, then we say that no assignment in this list is having a contest with XY, right? Now let us go for defining this legal, right? So if we have one empty assignment, that is always legal. Now define the recursive step, right? So first of all, we will divide the list into two parts, the first assignment and the rest of the assignments, right? We check whether rest is legal or not. If that is legal, we need to check whether X belongs to any one of these values, 1, 2, 3, 4, 5, 6, 7, 8, because we are solving a 8-pin problem. And also you need to check whether Y belongs to this list, which is having 1 to 8 value. And finally, we need to check whether XY is having no contest with the rest or not. Rest is already having, it's legal, right? Now we need to check that the first element that we took out is having any contest with the rest of the elements, right? So this is our first implementation. So let us try to execute this. So you see, we have got one empty assignment that is again is valid. We have an assignment like 1, 1 that is one valid assignment. I have got 1, 2, 1, 3, 1, 4. So you see, is this the kind of assignment we want? So what do we want as the final outcome? Any idea?
So there should be 8 queens.
There should be 8 queens. So what it is doing, it will give you finally 8 queens. But it will explore all the assignments starting from 1 variable assignment, 2 variable assignment, 3 to up to 8. And it will try out all possible combinations. So you see, this is not a very good design. So how do we make it a bit better? So we know that this X is a kind of list having 8 elements. So let us restrict this. Then these assignments will not be appearing, right? So how to do that? So let us define X to be a list consisting of 8 elements. Have I counted 8? I hope so. Right. So what it is doing, it is restricting the structure of X, right? So if we run this, you see that we have got 8, 4. So all these assignments are legal assignments. So this is a valid solution for 8 queens. So let us iterate through the other assignments. So we have this. Now, can you check these 2 assignments? Do you see any pattern here?
So they are just shuffled.
They are just shuffled. So that means the solution that you get here, it is a permutation of one valid assignment. So you can get multiple solutions, but most of the assignments will be merely permutation of trivial permutation of this one of the assignments, right? So can we do better? Can we do better? So what we know that our X is of the form something, say A1 by A2, and this is always fixed because we know that I am setting the queen for coordinate value of X equal to 1. So let me change this to A. That will make our life easier. So let us change this to A. So A is basically is a pattern like this. Now X is a coordinate, right? And it has 1, 2, 3, 4, 5, 6, 7, 8, all these values. So can we fix A with this? And so on and so forth. So in this way, what we are doing, we are fixing the ordering of X. And by doing this, we are not allowing the trivial permutations to occur in my solution. Right? So let us try to implement this idea. So here we are trying to implement this idea. So we are writing the another version where we have got these 8 queens X, where X is of this form 1, 2, 3, 4, 5, 6, 7, 8. We are imposing an ordering here. And then we are checking whether X is legal or not, right? So now we'll be calling 8 queens say A. So it is giving me 1, 4, this, and if we just check for, and you see this is not a kind of permutation of the first one as we had earlier, right? And if you can keep on doing this, but you will be seeing that they are not really permutation of any other assignments. Right. Now, other kind of optimization that we can do by setting. So now we have fixed the ordering of X. So this is not really required. So this we have already set. Because in my assignment, I do not have any assignment where the X coordinate, the two coordinate values are same. So that's why you can just remove this. And this is what we do not need to check. Right. Now let us rerun this. So you see, we'll be getting the same output, but what we have really gained to see what we have achieved. So I'll be using one function. The function is called time. So let me go to the first solution. So I'll just put this enter goal inside the time predicate. So what it will do, it will give us the total time, CPU time that it took to compute the solution, and also the number of inferences that the executor has performed. So if we just run this, okay, too many open queries, stop all and clear. Okay. Time. Oh, we need to put another. What is happening? Just give me a second. This. Just give me a time. I need to check the syntax. Time block. Okay. So this was the initial version. Okay. So now you can see there are these many inferences, lots of inferences, and it is having like 3.841 seconds, 100% utilization of the CPU. Now let us run the other one. So we'll be running the 8 pins. 8 pins, say we are running it for X. So you see the reduction in the number of inferences, it's huge. So it was in the order of billions, or I think it's billions. Now we are in the order of 10,000s, right? Now the third optimization that we did is to do away with this, then do away with this. Yeah. The number of inferences reduced a bit, like by 3,000, right? So you see that the same idea But we had played some tricks to come up with a very good efficiency achievement, right? So I think these are the things that we need to look for while we are writing Prolog programs, and of course, if you are writing bigger Prolog programs. So another problem that belongs to this particular regime is what we call as map coloring. So here we have got a map, and you are given with a set of colors, and to check whether with this set of colors, 4 colors or 3 colors, you will be able to color the map without any two regions having the, or neighboring regions having the same color. So this is the constraint that we are putting on the assignment. Now, this can also be solved using Prolog programming, but this particular problem that I'm trying to highlight here, it will be kind of a precursor of what we'll be discussing in our next module, which is basically on constraint satisfaction problem, which is our kind of subclass of the search problems, where we try to generalize the search algorithms as much as possible without having any dependency on defining domain-specific goals and domain-specific successor functions, as we did for the normal search algorithms. So with this, I will end this module on Prolog. But again, if you have any doubts or questions, I'd like to address on today's class.
Sir, the forward slash in Prolog is used to pair up to integers. Is that the case?
Yeah, so you can pair up different symbols with this forward slash. And while you want to divide will be written like this. So something like in, say, you divide this by n, for example. Right. So this is the division.
So that is integer division or the normal division, Victor?
I think this is integer division.
Okay.
So any other questions or doubts? Then if there is none, I'll be going to the assignment part. Okay then. So there is a set of 3 assignments that you have to work on. So I'll set the deadline in the MS Team message. So I'm not telling the deadline when you need to submit and how to submit. That we'll do later. But let us discuss the problems. But if you have any doubts on this, we can go on to discuss that. So the first problem is a variation of the ordered list program that we wrote in Prolog. So this, the earlier program that we wrote there, it either will check whether the list is in ascending order or descending order based on the fact how you have written this comparison, h1 greater than h or h is less than h1, right? But we want to write a predicate which is ordered list. It will not see whether this is in ascending or descending order. Any order will do. For example, list 1 and list 2. The first one is in ascending order, the second one is in descending order. For this both you have to output true, right? The same program will work for both ascending and descending order. The second program concerns shifting of a list by an offset. So here we are shifting, say, L1 by 2 elements, and the shifting is circular. So for example, if we shift this particular list once, then the outcome would be, so this 1 and 2 will be coming to the tail of the list, and this entire list starting from 3 to 8 will be pushed to the front. So it will be working in a circular way. And if you do another shift, you can see that 3 and 4 is being appended in the last, and the other elements are getting shifted in the front, right? The third program that you have to write to check whether two sets represented as lists, they are overlapping or not. And you know what do we mean by set overlap. And the second thing that you need to write, you need to use this set overlap predicate to define another predicate, which is set disjoint, right? So these are the three problems that you have to solve using Prolog, right? So this I'll be uploading on the MS Teams by today, and the deadlines and other submission protocols will be mentioned there. So is there any doubt on this assignment list? I think they are pretty straightforward.
So for the next week class test, so like we are not going to have this topic, right, sir?
No. The Prolog will not be there in the next week's test. It will not be there.
Okay, sir. Thank you.
Okay, then see you next week. Thank you very much. Thank you.
Thank you, sir.